All right, it's 2 after the hour. Abe, if you're ready, we can get going here. All right. Well, welcome everyone to another installment of our Lunch and Learn webinar series. Everyone's muted. You should be muted as you join the webinar. And I just ask you to remain on mute until the end of the presentation when we'll have time for questions and answers. There's also a Q&A function. Those of you familiar with Zoom, feel free to use that during the presentation as the questions come up, and I'll keep track of that and read them back. We are recording this session, and the link will be shared with you after the webinar, and it will also be available on demand to any NEBRA member. So that's really about it. Thanks again for joining us today to learn about the potential of urine diversion to get us closer to our sustainable agricultural goals. I'm so pleased today to have Abraham Noe Hayes with us. Abe is the research director at the Rich Earth Institute, which operates the nation's first community-scale urine recycling program, which converts human urine into fertilizer for use on local farms. You'll hear all about the initiative, but there's a lot of benefits. It saves water, prevents pollution, supports sustainable agriculture, and what we love at NEBRA, turning a waste product into a valuable resource. Abe coordinates a multidisciplinary research team and a demonstration effort involving farmers, scientists, planners, volunteer participants, as in urine donors, with the goal of developing tools to allow other communities to start recycling urine. Abe is a lifelong resident of Vermont. He has used alternate sanitation systems himself since 1976 and has been academically and professionally involved in their development since 2000. He has a BA in human ecology from the College of the Atlantic. So welcome, Abe. Thanks for joining us today. You could go ahead and share your screen. We are all very interested in hearing what you have to say, so take that away.
Great.
I'll stop sharing.
Thank you for that great introduction, and just pulling up my own screen here and we'll get started.
All right.
Seems a little bit laggy, but I'm sure it'll come along in a moment.
And I will
okay, here we go.
all right.
So can you see?
Yes, I can.
See that?
I'm going to go off camera. Thanks, Abe.
Okay.
Take it away.
Terrific. Okay. Well, thank you all for coming to hear and talk about urine diversion. I'm looking forward to everyone's questions and discussions in the Q&A section, because I think there's a lot of people with interesting, relevant, and diverse experience on this who are registered for this webinar. So looking forward to that conversation. But I'll start out with the slides, and as the title slide here frames it, we're looking at urine diversion for on-site recovery of nitrogen and phosphorus. So there's not a lot of on-site wastewater treatment nutrient recovery options. There are systems for nutrient removal on-site through nitrogen removal or phosphorus immobilization, but urine diversion has a lot of promise as an on-site system that actually recovers those nutrients. And we focus on the urine in particular because of what these different pie charts reveal. So the first one here showing volume. Urine is a tiny sliver, less than 1% of the volume of domestic wastewater. And yet it has about 3/4 of the nitrogen found in wastewater and close to 2/3 of the phosphorus, half to 2/3 of the phosphorus. And it also has a sizable portion of the pharmaceuticals that are in wastewater. About half of those are in the urine. And it's obvious to see why it's good to recover the nutrients. I'll talk about why it's also good to be recovering or diverting those micropollutants as well later on in the slideshow. And you can see the concentrations here are pretty unreal if you think about what's typical in wastewater. About 6,000 milligrams per liter of nitrogen and 300 milligrams per liter of phosphorus. When in regular wastewater, you're looking at maybe 30 or 60 milligrams per liter and just a few milligrams of phosphorus. So it's really quite concentrated. in the urine stream, which makes it a good place to capture it. And the quantity is quite high as well. If you look at the amount of fertilizer it takes to grow the wheat to bake a loaf of bread, it's the same amount of nutrients that are found in 1 day's worth of urine collected from an adult. So if we recycle the nutrients in our urine into fertilizer, we can actually produce a large fraction of the agricultural products that we need to support our society. So the Rich Earth Institute was formed to respond to these realities. And we have a vision, which is a world with clean water and fertile soil achieved by reclaiming the nutrients from our bodies as elements in a life-sustaining cycle. And in our work, we do that with the mission of engaging in research, education, and technological innovation to advance the use of human waste as a resource. So that's probably a pretty familiar concept to everyone attending here. The idea of biosolids recycling and urine recycling have a lot in common. Our origin is back in 2012. We had 60 volunteer recruits who did very informal urine collection for us. We gathered 600 gallons and did a proof of concept with a farmer partner and a $1,000 seed grant. It was very much a volunteer grassroots effort. And since then we've grown. We have now 180 full-time participants. So the number of participants has tripled, but the level of commitment is much higher, and the level of infrastructural investment is quite a bit higher too. And I'll get to what the infrastructure looks like later on. We're collecting 10,000 gallons a year and doing research that's funded by these different federal agencies and organizations that are shown at the bottom there. So our pilot project, or our flagship project, is the Urine Nutrient Reclamation Program. First of its kind in the US. We have permits from the Vermont Agency of Natural Resource through the Residuals Management Division and also the Wastewater Division. And the people who participate are motivated by 3 factors: water conservation, pollution prevention, and sustainable fertilizer production. Different people are motivated more or less by those different factors, but it's a sort of a synergy of these 3 different reasons people get involved, and so it's not just one benefit, one societal or environmental benefit that comes out of this. It's really those 3 legs of the tripod. And this cycle here symbolizes, or doesn't symbolize, it depicts the path of nutrients that accomplish those different goals. So we eat food, the nutrients leave our bodies in our urine mostly, and we sanitize that urine at high temperature. We use the product to fertilize crops. Those nutrients then flow into the crop being grown, and the cycle continues. So this is a project that is a pilot. It's a demonstration, but there's nothing about it that what I mean to say is this concept translates to any scale. So we're doing it on the community scale, but this could translate to the regional scale, or it could be implemented all over the country. Currently, the early adopters who are participating have these different attributes. They're geographically scattered, which means that that they don't all have to be connected on the same, say, neighborhood sewer. They're able to participate even though they're wherever they exist. It's not expensive for them to participate. They can use inexpensive urine collection tools, or invest more in a permanent system in there. I'll get to that in a minute. And they can choose how they collect, which you'll see in a moment, and we recognize them for their efforts. So we actually have the previous slide here. These folks down here got the Golden Funnel Award because they collected the most urine of anyone in the program, and we have this trophy. It's like the sports trophy, that every year is awarded to the winner, and it travels around for a year and then goes to the next person. So we try to really recognize people for the value of their participation, and it gets written up in the newspaper. There's publicity around it. People put awards on their walls. It's quite engaging how they get involved with that. So those are the elements that have allowed us to implement this as an inexpensively implemented early adopter model. So you could implement this in new construction. You could implement this across the board in a community, but I want to emphasize this, that it doesn't have to be planned from the ground up. It can be implemented in an existing community because there are very few barriers to participation, because the urine is so concentrated that we can transport it by truck from where it's collected to where it's processed in an affordable way. So this is what it looks like in a schematic sense to do urine diversion in the community. We have the collection on the upper left-hand side. This is the most informal version where people have these portable urinals, which is just, well, you'll see those in a moment, actually. Each of these is broken out. So this is an informal method. A more formal method are plumbed fixtures, urine diverting toilets or waterless urinals that are plumbed to small containers or large containers that we then pump out with our truck. And previously we had a septic hauler who pumped for us. Now we have our own urine truck that we use for hauling the urine. We bring it either to our central research location or to a farm. Currently it all goes to our research location, but we've also transported it to farms and treated it there. And then it is treated through pasteurization and applied to the field through a agricultural implement that distributes it. So what that looks like in photographs is this is one of these very informal collection containers. It's just a funnel with an odor blocking device and a 5-gallon container. You remove the funnel and screw on a tight fitting cap and then transport it to the urine depot. Women who can't urinate into, some women urinate into the funnel directly. Some put this device inside the toilet. It's used in hospitals for collecting urine, or they use this device called a P-style, which allows them to urinate standing into this container, and then they bring it to the depot. So this is very, very much for highly committed, dedicated urine donors who really want to go the extra mile to do this sort of extreme recycling. But then, oh, sorry, and this is where they bring it, is to the depot. And this is a location where there's this pump station. You place your jug on here, pull down this handle, and the wand goes in there and extracts the urine through a vacuum to a system that looks like this. It's a series of interconnected tanks. Here's the vacuum collection chamber. There's the vacuum pump. The urine is pulled up through here and then distributed into the tank. So this is for the people who are really wanting to go the extra mile to recycle their urine. The other approach is a plumbed porcelain fixture. So this works in a setting where people just want to use the toilet and the urine gets collected, but they don't have to do anything extra. And we feel like this is a very important next step, because some participants are as dedicated as the ones who I was just describing, but other folks just want to use a toilet. And most people, we believe, just want to use a toilet. And if it can recycle their urine, great, but they're not going to be moving jugs around. So, so this system is, these are both European toilets. This one has a divided bowl. Urine goes in the front. If you're seated, it goes in the front naturally. If you're standing, then you urinate in the front portion of the bowl, and it goes down a urine drain into the urine storage tank. This one has a clever trap where urine falls in the front. This image is a mirror image of what's above it. So if you're sitting down, feces falls in the back, urine falls in the front. It goes around this curved surface, and the teapot effect makes the low flow rate urine pull around that curve and go into the urine trap, while flush water at a high flow rate just shoots over that edge and flushes out the back. So it collects the urine, but not the flush water, even though there's no physical division in the bowl and it's totally hidden. And then it goes into a storage tank that has a pump out port that we pump out, and it's vented. It has a float alarm, and there's an overflow in this setting that goes to the sewer in case this tank fills before it's pumped. And this is a Vermont DEC approved innovative and alternative wastewater system design. So we've had this design approved, and we've had a number of individual site permits issued for these permanently plumbed fixtures that are in people's homes or in businesses. And so this is a way that these can be hard plumbed in permanently, and the user doesn't have to do anything. We just show up with our truck and clip on to the with a hose to the port on the outside of the building and pump it out through a hose onto our urine transport truck. And then we bring that back to our main center, our research and our processing center. We pasteurize it. This is a purpose-built pasteurizer. It's the only the only urine-specific pasteurizer in the world, as far as we know, and it uses electricity and a flat plate heat exchanger to heat the urine. And there's a computer control system that we engineered that maintains the proper temperatures and flow rates, and then it goes out into these large tanks where it sits until we can take it to the farms. And so here's the device, the applicator. It's got an 18-foot wide boom. It's pulled by a tractor and can distribute 500 gallons of urine at a time. And that's enough for about 1 acre of hay. So we show up and pump into this tank. Farmer takes it out, brings it back, refill the tank, and they go acre by acre and fertilize their field. And the effect is quite striking. So this center stripe here is a section that was fertilized using urine. And these two stripes adjacent were not fertilized. This one over here was fertilized at half the application rate. And so you can see the dramatic effect. This was our first year that we did field trials. Then the following year, actually the following few years, we did some controlled field trials comparing synthetic fertilizer to pure urine or diluted urine or no fertilizer. What we found was that, that urine was a direct replacement for synthetic fertilizer. And this bar looks shorter than that one, but the error bars actually all overlap. So we can't say for sure if either of these three treatments is better or worse than the others. They're essentially equivalent, which is good to know, because the conventional wisdom among people who use urine as fertilizer in their gardens primarily is you have to dilute urine to not burn the plants. But we determined that actually putting undiluted urine on didn't harm hay at all. And in fact, the yield statistically couldn't be distinguished from synthetic fertilizer or diluted urine. So now we only apply pure urine because it's a lot of work to pump all that extra water and move it around the field. Better to keep it as concentrated as possible. But the takeaway, I think, actually is that urine fertilizer can be a direct replacement for synthetic fertilizer and maintain equivalent yields. The question always comes up, what about pharmaceuticals? And I mentioned in that second slide that there are about half the pharmaceuticals that we excrete are in the urine, the other half are in the feces. So we're collecting half of the pharmaceuticals in wastewater in urine. And there's a host of them. We worked with the University of Michigan and the University at Buffalo to characterize those pharmaceuticals and to examine their fate when used in an agricultural setting. And so we used a suite of drugs that represent the drugs that are the right molecular size to pass into a plant potentially, so that can be taken up by plants. And they're also the ones that are most highly found in highest concentration in wastewater effluent. So they're not immediately degraded, and they're at high enough level in wastewater in general that they're detected in the effluent from wastewater treatment plants. And it covers all these different classes of drugs. So it's a good subset of drugs of all the drugs to examine when we're trying to see what drugs do in urine. And so we did testing where we used it in the field to fertilize crops, to fertilize lettuce and carrot crops. We tested the soil. We tested the groundwater that was in these sealed tanks that have soil in them. Rainwater falls through the soil, and then we can collect the water through these pipes from the bottoms of these tanks. And then we analyzed the crop tissue, the plants themselves. What we found was that using the highly effective and sensitive collection techniques that the University at Buffalo has with their mass spectrometer, they were able to detect several drugs, particularly over-the-counter drugs, but the levels were extraordinarily low. Caffeine was one of the drugs found at the highest level, and you would have to eat an entire pound of lettuce every day of the year for over 1,000 years to get the equivalent of 1 cup of coffee worth of caffeine from these plants. And the other drugs, the acetaminophen, Tylenol, or naproxen, those were all sort of in similar levels. So it was detectable, but vanishingly small, to the point where in a human lifetime, if you ate exclusively from this field, you wouldn't be able to actually even get a single dose of any of those drugs. So that was encouraging. On another standpoint, we looked at the ability of the nitrogen in the urine to actually be held in the soil and be available to crops, because that's another important agronomic consideration. And so we did some testing of applying urine and a urea control to test plots under different conditions, looking at how much of the ammonia evaporated versus what stayed in the soil to be available to plants. And that's a big issue because ammonia is really the only plant nutrient in urine or in fertilizer in general that's volatile and can evaporate and be lost in the atmosphere. And the losses can be quite high. In applying manure, for instance, like dairy manure, you can have up to 100% of the ammonia in that manure be lost to evaporation. If it sits on the surface of the soil and dries out, that ammonia is all driven off. What we found was that urine and urea pellets were pretty equivalent in how much ammonia was emitted from those. We measured that by putting enclosures over these test plots and then absorbing the ammonia out of the air in that enclosure into an acid trap and then analyzing the trap. So we found that similar amounts of ammonia were emitted from urea pellets on hayland, on grassland, compared to regular urine. And then there were 2 treatments we did to urine to try to limit that by raising or lowering the pH when the urine was fresh. So that prevents ammonia from forming in the urine before it's applied. And we found that both of those treatments showed reductions. Only the low pH urine actually was statistically demonstrated to be lower emissions than the other 2. But it's worth noting that over 75% of the nitrogen was retained in all 3 of these treatments, which is on par with or better than conventional urea pellets. So this is when urine is actually just applied to the surface of the soil, and then that can also be decreased by applying it into the soil when the soil is being tilled or cultivation is happening, or otherwise doing an injection system. But this is kind of the easiest way to apply it to hay, because you just apply it through that application system I showed before, where it goes in streams onto the soil and is then absorbed. So this was one variation in treatment we looked at was what is the form of nitrogen being put down. The other major one was what's the soil moisture, and this one's perhaps more telling and more useful, is that as the soil moisture increases, the ammonia emissions went down. And this is a very easy thing to measure in the field for a farmer to see how moist is their soil and apply it when the soil is more moist and not when it's more dry. It's also a better time to apply it because that's when the crops are actually growing. So that's our biggest recommendation in terms of urine application is don't apply urine to dry soil. Apply urine to moist soil. That's when the plants need it. And that's when the soil can actually absorb that and prevent the ammonia from being lost, because the thing that drives ammonia loss is evaporation of the manure or of the urine, and that is reduced if the soil is moist. So that's the method we currently use, is applying through that device, that liquid distribution system directly to the hay crops. But we're very interested in another potential option. And this is something that I've never included this in a presentation before. We've just been talking to folks at NIBRA, talking to folks at some biochar generators, and getting pretty excited about the synergy between biochar and urine, particularly between biosolids, biochar, and urine. And the reason that we think those 2 things are quite suited, and I'd be very interested to hear people's reactions in the discussion afterward, because like I said, we're new to this field, but we're excited about it because of the very different but complementary properties of urine and biochar. So urine has that ammonia, which is volatile, in which we can manage by applying it in appropriate conditions, but it requires management to avoid that volatilization. Biochar is very good at binding, at sorbing ammonia chemically onto the structure of the biochar. So the ammonia actually gets absorbed and electrochemically bound to the biochar so that it doesn't evaporate, even if it's sitting out and exposed to drying conditions. On the other hand, biochar, when it's produced, is very low in nitrogen, and it's also low in available phosphorus and other nutrients as well, I believe, but particularly nitrogen. And so by charging the biochar with urine, it becomes a better fertilizer. And I think that it's now standard practice when using biochar as a soil amendment to pre-charge it with nutrients, because otherwise it has a tendency to lock nutrients up that it takes out of the soil, and then that can negatively affect plant nutrition because the biochar acts like a nutrient sponge. So we want to fill that sponge with nutrients, and supplying those from urine is a great way to stabilize that ammonia from the urine and also get the other nutrients from the urine bound into the biochar so that it can be a complete fertilizer ready to be applied as a slow-acting fertilizer that adds organic matter and that immobilizes carbon and builds soil structure and builds soil health. So it seems like a big win-win. Maybe actually more, there's wins on many dimensions. And then biosolids biochar in particular is interesting to us because it is it's the other side of the wastewater handling. So we take the urine, we divert the urine out of the wastewater stream, but the solids still go into the septic tank or the wastewater plant, and they end up being sources of sludge in the future. And that sludge can be pyrolyzed, turned into biochar, and then recombined with the urine. It seems like a great way to make a agronomically and aesthetically and environmentally beneficial product out of those two flows that get divided at the beginning and recombined at the end. Then there are other methods that we've been following and are pursuing around making value-added products out of urine, and particularly concentrated products out of urine. So this one is being conducted in Switzerland by AVOG, which is a federal agency that is involved in water quality and wastewater management. And they've been working on urine diversion for a long time now. I think at least 20 years. I'm guessing off the cuff. I got a chance to visit them in 2015 and snap this picture and learn about their system. They use a nitrification system for urine. So this is a moving bed bioreactor, and they aerate that to turn half of the ammonia into nitrate, and then they distill it using a vapor compression distillation system. And it's a pretty energy intensive system. Straight distillation takes 710 watt hours per liter of water removed. With vapor compression, they can reclaim most of that energy, but it still takes over 100 watt hours per liter of water removed. Another 47 watt hours per liter of energy for running the pump for nitrification. But they get a 42 gram per liter nitrogen and 4 gram per liter phosphorus fertilizer out of the process. We took a different tack. We pursued reverse osmosis using an acidic pretreatment, because we had to make sure the ammonia, that the nitrogen stayed as urea and didn't turn into ammonia, because that passes through reverse osmosis. But we were able to get an energy consumption of only 32 watt hours per liter of nitrogen removed, compared to, again, 110 plus 47. So quite a bit of cost savings. Not quite as concentrated, but still, still within striking distance, and with much less energy. But an issue we found was membrane maintenance over time. There was a bit of a challenge on that. So we turned to a different method, freeze concentration. And this has some great benefits compared to reverse osmosis. There are no membranes to foul. It has no bottleneck in that sense, in terms of like small pores or something that sediment or biofilm is going to clog. Also, the concentration factor that's achievable is much higher. It's at least twice as high as reverse osmosis, just due to the maximum pressure that reverse osmosis systems can achieve. It does take somewhat more energy than reverse osmosis, but we've been learning a lot about latent heat recovery and implementing some innovations that bring the energy consumption down close to that of reverse osmosis. And we found that it has really excellent separation abilities for separating the nutrients from there's the section of the well, let me back up. Freeze concentration. The way it works is that we partially or totally freeze a volume of urine, and the ice crystals that form as we freeze it are essentially pure water. They may have inclusions of solute, but the crystal itself is a pure water crystal. And if we do this process correctly, inclusions are minimized, and the concentrate that's released when we start melting contains almost all of those nutrients. So we've frozen or partially frozen the urine. Then as we melt it, if we've partially frozen it, then what didn't totally freeze is still liquid that has all the solute in it. That comes out of the freeze concentrator as this concentrated fraction. Then as we melt it, the ice crystals, some of these inclusions that are also urine concentrate, but that were locked up in little ice cages, those melt out as well. We collect that, we recycle that into the next batch, and then the last 60% of the volume that comes out contains only about 5% of the nutrients. So this is a very, very nutrient reduced, very diluted stream that can be discharged as effluent, and the nutrients are kept in this first part. And we found that we get about 80% of the nutrients captured in 25% of the volume. And so you can see on this, that's what the second graph here is showing. As we melt more and more of the frozen urine, what percentage of the solute have we collected? And at the 25% mark, we've collected over 80% of the nutrients. And by the time we hit the halfway point, we've collected almost 100% of the nutrients. So this is a method that we've been piloting, or not piloting, rather, we've been trying on an experimental level, and we've gotten a 6.7 factor concentration factor in a two-stage process. So we freeze it, melt it, freeze it, and freeze the concentrate and melt the concentrate. And we've concentrated it at a factor of over 6 compared to the original urine, which is further than we ever achieved with reverse osmosis. This is just, I'll just skip through this quickly. This is just a graph of 21 different batches that we did on a 20-liter test rig, and looking at the distribution of solute collected over volume collected. And here's a picture of one of these experimental systems at the University of Michigan. So this one is in the basement of their the G.G. Brown engineering building. It's a newly renovated building, and they put in a urine diverting urinal and a urine diverting toilet that all flush down into this system. This is a laboratory setup. So this looks nothing like an in-practice urine diversion system would, because they have probes. We built this with probes, temperature probes, pH probes, conductivity probes everywhere, flow meters, and so it looks very complicated because it is. In reality, in practice, it would be much simpler. You would just have a collection tank, a freeze concentrator, and a product tank. This is an insulated box. Inside of it is a 2-chambered freeze concentrator that freezes one side and then uses the latent heat in that ice to be a heat sink to freeze the other side. So it alternates back and forth and reduces energy consumption by minimizing the temperature difference between the heat source and the heat sink side of the heat pump. Also worth mentioning, it says over here, acidification. There is a small dose of acetic acid of vinegar that's dispensed into the urine collection plumbing every time the toilet's flush, or every time the urinal is used. And that combats mineralization, because especially at University of Michigan in Ann Arbor, they have a huge amount of magnesium in their water. It's very hard water, and it causes huge problems for them in their urinals, their regular urinals throughout campus. They're always having to maintain the urinals because the magnesium causes the precipitation of struvite, magnesium ammonium phosphate, in the plumbing pipes. Our urinal is the only one that they don't have to maintain, because our small dosing of acetic acid prevents the ammonia from forming from urea and prevents that struvite from accumulating in the pipes. So this is actually the lowest maintenance urinal that exists on campus. So coming to the end of my slides here, with these experimental results, we generated a spin-off corporation called Earth LLC, and we got some funding, some seed funding from the National Science Foundation through their Small Business Innovative Research Program. So that has allowed us to develop a building scale urine collection treatment system that we're currently doing a proof of concept construction and testing phase of, that's been going on since last summer and wraps up this fall. It's this tool that allows on-site management of nutrient recovery that's on-site, and it makes a fertilizer product that is concentrated, pasteurized. There's a little mini pasteurizer that also has heat recovery that's built into this system, and is ready to use on-site or to be collected through a program like ours and then distributed to farmers. And it's this 4-step process that acidifies, pasteurizes, freeze concentrates, and then optionally charcoal filters. Because as I was saying about the pharmaceuticals, it doesn't look like the levels in crops are levels of concern, but as we know with biosolids, people have concerns that may not be allayed by data. And so so an additional charcoal filtration step is a good way, we think, to give additional assurance to consumers or to the public that that not only are the levels low to begin with of these pharmaceuticals, but then we have a step that even removes them further. Yeah, and the other ones sort of speak for themselves. I think this is my last slide, and I think it's a good time to now just switch to conversation.
All right. Thank you, Abe. I am already getting some questions. Let me see if I can, okay, if I can turn on the speaker. Well, let me start by, first of all, it seems to me you would have to have a sense of humor to be in this profession, and it's obvious that you do. Can I steal that that phrase, "P the change"?
Oh, you can. Yes, yes, and I'll tell our communications director. She'll be proud that it was stolen.
Oh, thank you very much, Abe. All right, we have a question from Harry. He says, I rent a house in Vermont during the winter that's 75 feet from the West River. Is there a way for me to participate in the urine collection program for 4 to 5 months per year? Not the whole year.
Absolutely. Yes, absolutely there is. And I guess probably you should shoot me an email and we can follow up on that. I think it'll depend on where you are, what town you're in, if you're within range of our collection service. And then also there's that depot in Brattleboro, and there's another depot that we're working on bringing online in Rockingham, the Bellows Falls area. And so that may be closer to where you regularly commute to. So those are options if you want to do it with that low-tech portable urinal system. But yeah, send us an email and we'll figure out what makes sense given your location and how much you want to invest and how much you want to be involved in the transport process yourself.
Well, that's great. I'm glad we're getting you some volunteers.
Oh, and there's your answer. You drive through Brattleboro. Yeah. So the email would be info@richearthinstitute.org. Or if you want to put your email here, I can email you.
How do you normally recruit participants?
A lot of it is word of mouth. So people
Okay.
just hear about us from friends, or they're at someone's house and they're like, what's this? Or why does your toilet have this divider thing in it? And then we also do outreach at public events, at the local farmers market, through local organizations that invite us to do presentations.
Thank you. All right, yeah. Another question we have. Oh,
okay.
Go ahead.
Oh, one other thing I'll say actually is that some of that outreach effort is funded through the National Fish and Wildlife Federation and through their Long Island Sound Study Program, because they're trying to pursue all options for reducing nitrogen emissions into Long Island Sound. And so they've been underwriting expansion of our collection program into Bellows Falls, and part of that is an education program. So so we're very proud that we were selected by them 2 years in a row to be a novel and promising nitrogen mitigation strategy.
Yes, congratulations. All right, here's a question. How about odors? Does pasteurization mitigate? How long is it stored at collection locations?
Great. So pasteurization doesn't really change the odors. We mostly manage odors through how we store and how we apply the urine. So and how we collect it. So for collection, the built-in systems with the standard, well, not standard, but with the porcelain fixtures, there's no odor in the bathroom because there's a trap in each of those fixtures, just like a standard conventional fixture. So no odors in the bathroom because there's no way for the gases to get into the bathroom. Same in where the storage tank is in the basement is vented to the outdoors. In terms of if you have that informal collection system, the portable urinal, it has a little odor blocking device in the funnel, but there is some air displaced from inside the container when you use it. So some people have it in a well-ventilated room. Other people add a little bit of acid, whether it's acetic acid or citric acid, to the container before they start using it. And that prevents the urea that leaves our body from hydrolyzing into ammonia. And that ammonia is where the really strong odors come from. And I think that the low pH also stops other odors from forming. So there's really, the urine doesn't transform. It stays fresh, essentially. It's pickled if you have that acid. And so then even the small amount of air that's displaced when you use it is not noticeable. I think the place where the odor is most unavoidable is application to farm fields, but that is a lower odor than liquid manure. So if you've ever driven past a farm when they're pumping out the lagoon and applying there, it is powerful. And with the urine, we actually apply to a field that's adjacent to my house, and so we get a little whiff of it the afternoon it's applied, and then it's gone. So we've never had any complaints about that. I think on the level of farm odors, it's pretty minimal. People do use it also in their gardens a lot, and if anyone's curious about it, we have a document on our website under publications, I believe, that's called Home User Guide or Home Use Guide, and it talks about the health and agricultural considerations around using urine as a fertilizer. And what most folks do with that is they apply the urine and then they would water it in with a hose, and that really washes the urine and the odors down, and you don't have anything that lingers. And it's a powerful fertilizer. It's something if you want to try it at home, you'll be impressed, I think, regardless of your expectations.
How about collecting my dog's urine? Because that makes spots all over the place.
Yeah, I'm not sure how you do that, but that always comes up. Yeah, and I don't know why the dog urine burns, because human urine, unless you put it in one place, maybe it's because it's concentrated. They just go in one spot if the soil is dry, but we haven't seen that with human urine.
All right, we got more questions for you, Abe.
Okay.
Here's an interesting one. Does taking a bunch of vitamins daily adversely affect the urine?
I don't know about vitamins. I don't know why it would. Vitamins, I don't think, are known to have any adverse effect agriculturally. People usually ask us about pharmaceuticals, but I sort of adjust our understanding around those. There is some interest from some of our research partners about whether vitamins in urine could actually have a beneficial effect on nutrition of crops. I'm not really sure if that is something that would happen, but I've never heard anyone talking about adverse effects.
Huh. So it is, but maybe some future research.
Yeah.
All right. Another question is, what is the business case for parks, businesses, et cetera, to participate as donors? Is the market stable enough to justify upgrading buildings and plumbing? And where do you see it going over the 10 years? Yeah, I was interested in that too, as far as retrofitting facilities.
Yeah, I think it would depend a lot on the water and wastewater situation of a given building. There currently, I think the economics are such that if you need to manage nitrogen or phosphorus in your wastewater, then diverting urine is a very cost-effective way to reduce those levels in your wastewater. If you don't have to manage those things, then there's not a direct economic benefit to the user, with the exception of maybe a lower water bill if you're using waterless urinals instead of flush urinals, for instance. But what we've seen mostly is that businesses that have begun adopting this is that they have an environmental value system, and they want to reduce the nutrient pollution that they're causing, and so they do this as one of the investments they're making in their environmental footprint. What we offer in the Brattleboro area is a collection program, and it's a pretty affordable collection program. We actually do it mostly on a sliding scale, but if you're not near someone who is able to collect the urine and beneficially reuse it, then that is also something you'd have to figure out, is what are you going to do with the urine once you have it. We have some partners in Long Island and in Cape Cod where they're facing a lot of pressure around nitrogen, who are starting pilot projects with installations and with recycling services. So that's something that hopefully we'll see growing, especially in these nitrogen impacted areas of infrastructure, physical and business infrastructure, of someone you can call and have them pump your urine tank and reuse it. I think that it's a great area to be thinking about in terms of people who are already recycling organics or recycling nutrients, or these materials that none of them have a lot of dollar value when you collect them, but they cause trouble if they're not managed properly, and there are users who want to have them if the process can be streamlined. So our vision long term definitely is that commercial haulers would be collecting urine, probably for a fee, and then producing a product that would be desirable to farmers or gardeners or other end users.
Very interesting. And it kind of
oh, go ahead. Yeah.
No, there's a related question, so you can finish your thought.
Okay. Yeah. So I should make the point that our research that we're doing into the handling, the materials handling and the processing of urine, we do it as a pilot project, but we also do it as a way to figure out what works and what doesn't, so that other people who may want to get into this as a business venture or as an organization or a nonprofit that doesn't have a lot of resources but wants to do this same sort of project doesn't have to reinvent all these wheels. So there's another document on our website under publications that's what's it called? Community scale or urine. I should know what it's called, but it'll be obvious. And it's a in-depth discussion of all the different methods we use. That's where those diagrams came from, for the collection, the transport, treatment, and the application of urine. So that we're trying to sort of share all of our secrets on how we make it work.
So the next question is about, it seems to me that you got the technical stuff down. It seems like the logistical stuff is really what's kind of the barrier. And that's what this question is about. How might urine collection systems be implemented in urban areas where more people are renters living in multifamily buildings, and transportation to farms is more challenging? And of course, the trust in local government is pretty low compared to Vermont. Someone was pointing out.
Yeah, I think that COVID has been such a striking example of how much trust there is in our government in Vermont. I was really amazed hearing other states and Vermont in terms of people listening to guidance and acting on it. So I think that's a great point. Vermont is different from a lot of other states in the country. In terms of urban settings, it's definitely easier to implement this in new construction than in retrofits. And so where we're focusing in terms of buildings and green buildings, especially green buildings, is in the initial construction, because then we're not paying to replace existing systems. I think that the lessons that we learn in new construction will probably make it more cost effective to put urine diversion into existing construction, but definitely the place to start is new buildings where those costs can be minimized, and where they can be designed to have multiple points of inspection and clean out for the plumbing, and build into the system direct runs for collection, for pump out and storage. So yeah, I think those logistical concerns are real, and I think that that any new infrastructure technology, there are going to be questions about, well, how will you implement this in different locations and different scales? And our approach in Vermont has been to start building it and see what problems we find. So we knew there'd be problems, we didn't know what they were, and we've learned, okay, there's certain kinds of pumps that aren't appropriate. We talk about that in our guide. There are certain scales of the application equipment that farmers need for it to feel like it's a reasonable use of their time to pull it around and refill it. And I think that those same questions would come up with working with building engineers and working with developers. We just haven't really explored that area yet.
Thank you. And then there was just one comment, which said, ironically, for rotors, when septage or biosolids are lime stabilized to a pH greater than 12 to reduce pathogens and vector attraction for land application, that high pH ends up driving off ammonia.
Yeah, and that's very true. And the reason that the difference in high pH treatment for urine is that the pH is raised before the ammonia even forms. So when the urine leaves our body, the nitrogen is mostly all in urea form. Some of it is protein and organic material, but most of it is urea. And the urea only turns into ammonia when urease, the enzyme urease, is present and the pH is in the correct range for the urease to function. And so, so the low pH definitely inhibits urease functioning. I think it also inhibits the creation of urease by the bacteria that produce it. But even if urease is present, it's made ineffective by low pH or high pH. And so then the urea stays as urea, and the pH doesn't affect, high pH doesn't drive urea off as a volatile because urea is non-volatile. It can't evaporate. I guess it's too heavy a molecule. I'm not really sure why it doesn't evaporate, but it doesn't. And so it's sort of counterintuitive to anyone who's in the wastewater or the biosolids industry, but it's because that transformation has been stopped from happening. Now it's a little bit tricky to manage that because the pH has to be raised pretty much immediately. So if urine flows through a long pipe, flows 50 feet through a pipe and drips into a container, in that process, in the pipe flow, the hydrolysis of the urea into ammonia can happen even as it travels through the pipe. So you really have to dose at the fixture with the high pH agent, or have the urine going into a collection container with a very short pipe. So people are still working on the practicality of how to implement that approach.
Well, very good luck with that. I think that's all the questions that we got today, Abe.
Okay. Could I pose a question to the group if anyone has any thoughts on biochar made out of biosolids and in any capacity? We're really trying to sort of find out what's going on in that area these days and gauge people's opinions on how these ideas that I mentioned, how much those are rooted in reality.
If anyone, you can raise your hand. I can maybe be able to let you talk if you want to react. But I'm very excited about that, as you were, the potential synergy with the biochar. And I would be happy to give you a list of our members who make biochar, and as well as some researchers that I know that are working with it.
Terrific.
Here's another question, or a comment, I guess. People are interested in pyrolysis as a way to reduce, yes, it's a PFAS focus right now, and pyrolysis is getting a lot of attention. And there is a lot of potential. That's the one technology I see a lot of potential in right now. So that synergy would be awesome, and we'll keep chatting. We'll make that happen. Another question. So just people wanting more resources about biochar as well. Jose, I will follow up with that as well. Hang on, getting some more stuff here. Yeah, all right, thanks. Eamon's just letting us know. Yeah, the science isn't really final, but there's definitely a lot of potential with the pyrolysis. So good luck with that, Abe.
Great.
And
Well,
again, let me know if you need any other resources after I send you the initial batch here. one more question, I think. Nope. Okay. Thanks. All right. So that's all the questions. And this has been very interesting. Thank you, Abe. Thank you, Rich Earth Institute. And best of luck to you.
Thank you
as
very
you go
much.
ahead. Yeah.
Thanks for everyone for joining. I'm really
yes,
great
thank
to
you.
have you here.
Thanks for joining, everyone. We have these sessions lined up through October, so please check our calendar. Let me know if there's something you're dying to hear about. I'll make that happen. And with that, I'll let you all start your weekend. Thanks again, Abe.
Right.